Hello, and thank you for joining us here today. Our webinar today will cover the following topics: differences between flash and preparative HPLC, the importance of matching columns, what are scouting runs and what information can you get from them? If you create a method on an HPLC, how can you get it to flash? Compound-specific compound optimization, how can it be used for flash? And if you are lucky enough to have an ACCQPrep, it can create flash gradient methods for you. The major differences between flash and prep are due to the difference in particle size, and that drives all of the differences between the two techniques. Particle size affects resolution. Larger particles means lower resolution. The need for higher resolution has driven the need for smaller particles in HPLC and UHPLC. However, smaller particles create higher back pressure. This higher back pressure affects everything else in these tables. For flash chromatography, we can either do solid loading or inject directly onto the column because of the lower back pressure. An HPLC system uses an injection loop, which is switched into the flow. Flash chromatography has higher flow rates. For example, a 50-gram C18 column runs at 40 to 60 mils per minute at about 4 bar, while a similarly sized 20 by 150 millimeter HPLC prep column is more typically run at about 20 mils per minute, which generates around 83 bar back pressure. The lower back pressure allows flash columns to be made of plastic, but HPLC columns must be metal. Flash column packing is easy, while HPLC columns must be packed at high pressure to prevent the packing from settling and creating voids under pressure when the column is run. Beyond this, the chromatography is similar, and so we can develop methods on HPLC systems and transfer them to matching flash columns. One thing that affects all gradient calculation and all method transfer is the use of non-matching HPLC and flash column. All C18 and all other reverse phases are not the same. The runs here use the same gradient methods. All the columns were the same size and the same sample was used. The elution on these columns is very different. The different retention times resulting from the different column selectivities would generate different and incorrect retentions when the method is transferred or calculated to any prep LC system, whether flash or HPLC, if it did not use the same column chemistry. Teledyne ISCO has matching analytical and preparative HPLC columns, which also match the flash columns. We have C18, C18AQ, and C8 chemistries. This is an example of method transfer using matching ready subcolumns. A customer's cyclic peptide was transferred from an analytical HPLC to a flash column. A C18AQ column was used, and the method was easily created on the CombiFlash NextGen 100 system. There are several ways to purify compounds on flash. The standard gradient method on your flash system is good for rapid cleanup of well-resolved compounds, but may waste solvent if the compounds elute early in the run. TLC plates are often very slow to develop, especially for solvent systems containing more than 50% water. Another technique is iteration. Start with a standard method or a scouting run. Flatten the gradient by guessing at the gradient start and end points. Run the new gradient, look at the retention time, and adjust the solvent composition at the start and end of the gradient. Repeat until the chromatography looks good. This uses a lot of time, solvent, and sample on a flash system, but it uses less solvent and sample on an analytical system. So an HPLC is commonly used to develop the method which is transferred to the flash system. A scouting run is a very fast gradient from the weak to strong solvent. Speed is often more important than resolution. The gradient is intended to give a quick look at the chromatography. We are looking to see if the column and solvents will work well. We determine if they work by looking at the peak shape, the resolution, and retention time. The resolution tells us if the compound can be run on flash or if preparative HPLC is required. The retention time lets us determine the solvent composition for the gradient endpoint. This gradient was run on an ACCQPrep HP150 using a 20 by 150 millimeter ReadySep Prep C18 column. It is a mixture of capsaicins. We will use this example of the information we can obtain from the scouting runs. The desired peak elutes at about 7.5 minutes. But there is an impurity that elutes very closely to the desired compound. Can we purify it with a flash column? How can I tell? On an HPLC, if you can see the impurity in the scouting run, it can be resolved as shown on the run to the left. For flash, you may not be able to purify the mixture. A capsaicin mixture was chosen because the compounds are barely resolvable on C18 flash on a small column. In the run on the right, a 5.5 gram C18 column was used with a 1% load. There are many ways to create a focused gradient. The final gradient is the same no matter which method is used, so this calculation is usable no matter how you create a method. There are many scouting gradient methods that people can use, and we present a general equation that is useful for any HPLC system and most scouting gradients. Most users have a standard scouting gradient used for columns of a given length and inner diameter, so most of the math only needs to be calculated one time. Our experiment with the capsaicin showed that gradient and HPLC, we need more than 0.2 minutes resolution to resolve the compounds on flash chromatography. We can make the equation general for any LC system by converting the difference in time to a difference in %B. If we are in the linear region of the scouting gradient, we can convert the difference in time to a difference in solvent composition. We do this by determining the slope of the gradient. The slope is the ending solvent composition minus the starting solvent composition divided by the gradient time. Do not include the isocratic hold at the end of the gradient in the calculation. In this case, 100 minus 5 makes 95. Divide that by 6 makes 15.8% per minute. We need 3% resolution, but your HPLC labels the peak with time, not %B. Divide 3% by the gradient slope to convert from delta %B to delta time. In this case, we calculate about 0.2 minutes as we would have expected. So compounds eluting less than 0.2 minutes apart need preparative HPLC. And if you go to the Teledyne ISCO website, find application note number 119, and it will describe all of these equations as well. The advantage of using HPLC is that it uses less solvent than the flash system for method development. A UHPLC uses very little solvent. There are 3 main steps to determine a method for flash. First, determine the column volume on the analytical system. This only needs done once. Columns of the same length and inner diameter are sufficiently close in column volume for our purposes. Next, develop the method on the HPLC. Finally, scale up to the flash column. Application note number 118 describes the scale up. Sometimes the column manufacturer lists the column volume. I like to use a salt that absorbs UV light because they elute at the void volume at low organic concentrations. The void volume is very close to the column volume. I also ignore extra column volumes such as dwell volume ahead of the column and the volume from the column to the detector. I calculate the column volume by dividing the void volume by the flow rate. Next, develop the method. Note the solvent composition at the start and end of the gradient. Also, take note of the gradient length and flow rate. I like to use column volumes as a unit of measurement. Using column volumes allows scale up to any size flash column without regard to flow rate. Flash columns list the column volumes because of method transfer from TLC, so the information is easily obtained. Flash systems allow method development as column volumes, and also they can run as column volumes, so column volumes are easier for scale up. This run used a 4.6 by 150 long column at 1 mil per minute. The start and end of the gradient is the same as that used for the HPLC method. The gradient length is the same as the analytical run, but in column volumes. The compound eluted the same on both runs, about 3/4 of the way through the total gradient distance. This also works with UHPLC, a ReadySep 2 by 50 millimeter C8 column. A ReadySep 2 by 50 millimeter C8 column. I used a 12 CV gradient on the analytical column and transferred it very easily to the 50 gram ReadySep RF Gold C8 column. I like to use a standard gradient length for my HPLC runs because I know the gradient length in column volumes, and I can scale to any column size, including the 8.6 kilogram columns. The method transfer is affected by dwell volume, especially the small flash columns. Dwell volume causes later elution because the gradient is delayed. Scale-up only works well if the column chemistries match. Compound-specific method optimization is very commonly used. I see similar charts as shown in this slide in many labs, but for their prep HPLC. I tend to call it zones because the scouting gradient is divided into different zones. This is very easy to understand, but it takes a bit of time to create the zones and methods. A change in either the analytical or prep system the zones need to be created again because of differences in dwell and column volume. This means that if you have the zones defined for your preparative HPLC system, they would need to be redefined for your flash chromatography system. You would also convert the prep HPLC methods to column volumes to allow for different flash column sizes. Each zone defines a different gradient method. Despite its name, this method isn't specific to any compound. This peak or this peak would elute late in the focused gradient, while this peak would elute early in the gradient and may not be well resolved from early eluting impurities. Another technique that is sometimes used is the accelerated retention window. C is the solvent composition to elute the compound. RT is the retention time in the scouting run. B and delta are offsets to set the desired retention time and also include gradient delays. It can be very accurate, but a change in analytical, prep system, or scouting gradient requires determination of a new instrument constant. The previously described methods are complex. Zones needs the limit of each zone to be determined and tested. The time on target algorithm is a simple determination of all of the parameters with a single scouting run used in the previous methods. It is built into ACCQPrep systems. A change in gradient or analytical system only requires a new scouting run for calibration. Like the accelerated retention window, the time on target algorithm determines a focused gradient specific for the desired compound, but the gradient is better optimized for that compound with the time on target algorithm. Why would you use this method? The calibration is simple and needs done only once. A change to the analytical system just needs a new scouting gradient for calibration. If there is no matching analytical column, the scouting gradient can be run on the ACCQPrep with the prep column and a tiny amount of sample. This can be run on the ACCQPrep only, or you can use the data from an analytical HPLC scouting run commonly used to document a reaction. To use a column on the ACCQPrep, select Column and Scouting method. A 150 millimeter long column will have a 6-minute gradient. Other column gradients will be in proportion to the column length. The focus gradient generator is very easy. Do a scouting run, select the peak you want to purify, and then purify the desired compound. The completed run shows a focus button. Focus opens another screen. Choose the peak to be purified. Select a matching column for purification and select the desired peak, and then press focus in the new screen. The system will generate a focus gradient centered on the desired peak. The compound typically elutes in 5 to 8 minutes, which increases resolution and loading. A wash step is included, which may be removed for more time and solvent savings if the sample is known to be clean. A focus gradient can be created in the Q screen and run with other samples if an auto sampler is used. On the ACCQPrep, it is very easy to determine a focus gradient from an analytical scouting run. After calibrating the analytical scouting gradient, just run the same scouting run for your samples. Enter the retention time for the desired compound, and the ACCQPrep will calculate a gradient for you. So, back to flash chromatography. How does all of this help us? You run the scouting gradient on the analytical HPLC or ACCQPrep. Determine if there is enough resolution for flash chromatography as described earlier in this slideshow. Calculate a gradient. If there is enough resolution for flash, transfer the method to flash. Application note number 119 has the details of scale-up as well as this table. The gradient method listed here changes the gradient length as a function of column size. Dwell volume affects small columns more than larger ones. All of the runs will purify compounds within just a few minutes. The next several slides will show how scouting gradients can alert us to chromatography issues in the preparative runs. The most common one is pH control. A scouting and preparative gradient for quinine with no modifier is on the left, and corresponding runs with 0.1% TFA are on the right. Look for good peak shape. Look for fronting or tailing. In this case, quinine was tailing and the compound came out too early without a modifier in the preparative run. If it looks bad during the scout run, it will look worse in the focus gradient no matter what calculation method is used. Acidic compounds can also behave strangely. Here are scouting and preparative runs for salicylic acid and water methanol, but a TFA modifier again was used for the runs on the right. Again, the peak shape in the scouting run suggested the preparative run wouldn't work well. In both the acidic and basic compounds, the peak shape was improved and the gradient calculation worked when a modifier was added to the mobile phase. The idea is to force the compound to be in one form or another, either all ionized or all as the free acid or base. Common method development problems include the pH may not be good for the compound chemistry as just shown. Verify that the same solvents and modifiers are used on the analytical and prep. Verify matching columns are used. One or both of the columns are worn out, which cause a change in retention time, thus a change in the gradient calculation. Changes in scouting runs. Changing an instrument means a different dwell volume, so the gradient is delayed differently. Now we will open the floor to questions.
Well, thank you, Jack, for sharing your expertise. And we would like to welcome you to enter any of your questions through the Q&A function within Zoom. And with that, I will turn it over to Jack.
Hello, and thank you for your time today. The first question is, you said that matching columns are important. However, I do not own a Teledyne ISCO flash system. Will your columns work? And the answer is yes. Our columns will work on any chromatography, any flash chromatography system. And within the next 2 weeks or so, I will have an application note describing that. The next question is, when you use a scouting method, are you worried about sample loss? The answer is not really, because my scouting methods are either run on a analytical HPLC, which uses only microliters and micrograms of sample, or if I need to run it on the ACCQPrep, I only need maybe 1 or 2 milligrams for the scouting gradient. So I don't have very much sample loss. And if you use the ACCQPrep, you could still collect the fractions and then recycle that material. So that's a good question. For the scouting analytical method, do you need a different sample loop? The answer is, if you're working off of an analytical system, an analytical HPLC, you really don't. If you're using the ACCQPrep, the answer is no, you really don't, because it's last in, first out. And the focus gradient generator on the ACCQPrep takes that into account. So you actually can get by with a very small injection and still get very good results. What can you do if the scouting run cannot generate a prep method? I'm assuming that in that case, the compound is eluting very early. And what you do is, when you do the run, you know what percent B that you started with. Okay, so you would run a gradient starting with that same solvent composition at the start, and run for about 12 column volumes and end at about 20% B higher. Usually the system can't calculate a prep gradient because the compound comes out very, very early. We know it elutes, so running a gradient with that range, it will still elute. For scouting methods on the ACCQPrep, if you're worried about sample loss, can you run the scouting method on a smaller column and then run the purification on a larger column? And the answer is absolutely. My preference, it really works really well if I run, like, say, a 10 millimeter column and I only need a small amount of sample. And then when you run the focus gradient generator, you could tell it which larger column you want to use. Another question I have is, can my flash system run with buffers the same as my HPLC system? And the answer is yes, it can. When you get done running in reverse phase, you want to wash the buffers out so that there's no chance of the buffer precipitating when someone tries to switch back to normal phase. And the other thing is, if you run buffers all of the time on your flash system, the pump seals will wear out a little bit faster. Other than that, there's no harm to the system at all. have any other questions? We'll keep the questions open for just a minute or two more. Another question is, I don't use an isocratic hold at the start of the run. Why is that? And truthfully, I never found the need for one. The grow volume in your HPLC system does make enough of a isocratic hold at the beginning of the run that I don't need one. And the isocratic holds might interfere to some extent with the focus gradient calculations.